Okay. Hi, this is the final project of 5800 Summer 2023 online shopping recommends. There are three people in our group. My name is Tianshu Yang, and there are two also of our group mates.
My name is Ruixin Li.
My name is Zichuan Zhu.
So there are three main parts of our project: introduction, analysis, and conclusion. Let's first look at the introduction part. In the dynamic world of online shopping where customer satisfaction and sales rules roost, personalized product recommends are the keys. Imagine getting recommendations based on your likes and history. That's a buzz. And the secret ingredient is the algorithms. The Ford-Foxon algorithm, which is known as optimizing network flow problems, can enhance efficiency by doing personalized recommends and improve overall user satisfaction. Let's look at the question and our goal. Our project seeks to answer how can we amplify the impact of network flow algorithms, such as Ford-Foxon, with efficiency enhancement to refine personalized online shopping recommends. We're diving into solutions that fine-tune product suggestions, aiming to optimize the flow of personalized recommends and elevate user satisfaction. Now let's look at the analysis. What we did is, in general, we can see the problem as a max flow problem, where the flow represents user satisfaction, and based on this, we can build the recommendation graph, use Ford-Foxon and its bed version Elements Carp to do the code implementation, and we will analyze limitations during this process. Let's see how we build the recommendation graph. The scenario often involves recommending a single product to multiple users, which creates a many-to-one relationship, or as we know as the assignment problem. We use bipartite graph to represent this problem and seek the max flow, where flow magnitude signifies user satisfaction. As we can see from the graph above, the source node represents the starting point of the flow, often represents the unsigned users or users who haven't received any product recommends yet. And the flow from the source node to user node signifies the allocation of recommends to these users. On the other hand, the seek node on the right represents the endpoint of our flow. The nodes correspond to assigned products. Flow from user nodes or other nodes representing products coverages at the seek node indicates that the products have been successfully assigned to users, and nodes representing and in the middle, nodes represents users and products linked through edges symbolizing potential recommendations. Let's look at the edge capacities. The edge capacity from source node to each user is set at 1, reflecting one user, one product allocation. And edge capacities from products to sync relates to assignment frequency. While in the middle, edges between users and products get capacities based on user-product interactions. For example, it can be user-product view, click rates, and etc. And we can use Ford-Foxon algorithm optimally matches users and products by maximizing objectives on the capacity constraints, ensuring a efficient personalized recommendation system, and improvement of user satisfaction. In the following part, my classmate Zichuan Zhu will introduce the code implementation of this graph. Zichuan.
Okay, here's the implementation and improvement we use to solve this problem. So for the Ford-Foxon algorithm, it is used to solve the network maximum flow problem. Here's the implementation. The first BFS function. We use this function to find the augmented path from source point S to target point T in the residual network. And the parent array is used to store the path information, which is the parent node of node V, and we will return true if a path from S to T was found otherwise we will return false. The second is the Ford function function. First, we copy the original graph and then we find the path from S to T through the parent array and find the edge weight in the path, and update the weights of all edges in the path based on the flows we found. And we add this flow to the max flow. Finally, we return the max flow. And the last part is main function. We define an adjacent matrix for a directed graph, and then we call the Ford function function to find the maximum flow in the graph and print it out. But there are some limitations of this approach. Uh, First, we should know that Ford function does not inherently guarantee that users are matched with their most interested products. And if the capacity of an edge is not an integer but a real number, the algorithm might get stuck in an infinite loop. Also, the time complexity of this algorithm is O max flow multiply E. So when the maximum flow is very large, the algorithm can become very slow. To improve this, we decide to change to the Edmonds-Karp algorithm. Besides all of this limitation, we also have some limitation on the code. For first, the graph size is fixed at start, so this is leaks of flexibility. And we use adjacent matrix, which is memory intensive for sparse graphs. Adjacent list might be a much efficient way. And there's no dynamic memory allocation if the graph are much larger than the defined size. This approach may not cannot handling larger graphs. And the last, this approach lack of modularity. In the code, everything is placed in one file, but it is beneficial if we split different components into separate modules or classes. So here's the improvement, and we use the Edmonds-Karp approach, modification based on the limitation we list. So first, in the graph class, we present a graph. This is much better for we split the components into separate modules and classes. Second, we use the BFS method to check the existence of an augmenting path in the residual graph. If such a path exists, it will return true and update the parent vector with the path information. And for in the third, max flow method. In this method, we use the Edmonds-Karp algorithm uh, to calculate the maximum flow from source S to sink T. It calculates the path's smallest residual capacity along the path and updates the flow in the residual graph accordingly. The process is repeated until no more augmenting paths are found. And for the main function, we enter the numbers of vertices and edges. For each edge, we provide edges start vertex, end vertex, and capacity. Then we specify source and sink vertices. Finally, we will get the maximum flow. So as for the Edmonds-Karp approach, the heart of this code is this algorithm. By always selecting the shortest augmented path in each iteration using BFS, it ensures the finite termination of the Ford function, and the time complexity of this algorithm is VE squared. Next, my team member recently will talk about the comparison of algorithm and the conclusion of our project.
There are some advantages and disadvantages for both Ford Fulkerson and Edmonds-Karp. The Ford Fulkerson algorithm offers simplicity in implementation and continuously flow increases as long as augmenting paths are available, but it lacks termination guarantees, especially with non-integer capacities or suboptimal optimal path choices, and can have extended runtimes. In contrast, the Edmonds-Karp algorithm guarantees maximum flow discovery in finite time by always selecting the shortest augmenting path. However, its computational time can be slightly longer due to its focus on shortest path. which might pose challenges for large-scale problems. And now this is the last part of our presentation, the conclusion. And there exists some limitations in our project. The first is the simplicity of the model. The program's basic representation doesn't capture the complexity of real-world recommendation system. The second is the limited recommendation factors. This program overlooks advanced recommendation techniques like user preferences and machine learning. The third is the static data. The program doesn't adapt to changing user behavior unlike the real systems. And the fourth is the time complexity. Since Edmonds-Karp time complexity might be slow for large graphs, there exist some other algorithms that might run faster. And the last is that there are no error handling or input validation for our project. In summary, our project has shown how smart algorithms can make online shopping better for users. By studying how the Ford Focusing algorithm and the advanced CARP algorithm can improve product suggestions, we've seen how technology can shape the future of online shopping to match what users want and need. This is the end of our presentation. Thank you.
Okay, thank you, bye.